Our next clip deals with atmospheric moisture, or humidity. We have learned that evaporation and evapotranspiration transfer water from the ocean, surface water, and plants to the atmospheric moisture pool. Now we'll discuss atmospheric moisture, humidity, in more detail. First, a definition. Humidity is the amount of water vapor in the air. There are several different ways that humidity can be expressed, and I've listed a few here. Absolute humidity refers to a mass of water in a particular volume of air. Specific humidity refers to a mass of water in a mass of air. Because air can change volume as it rises and falls, because it expands and gets compressed, we are generally going to see specific humidity referred to when we're talking about rising and falling air. The third way that we express humidity is relative humidity. And relative humidity for us is going to be far most important. So we're going to look at relative humidity in much more detail. Relative humidity is the ratio of the amount of water vapor that's in the air compared to the maximum amount of water vapor that the air could hold at that temperature. Notably, relative humidity is expressed as a percent. It is telling us how full the air is with water. Relative humidity reflects the amount of water vapor in the air relative to the amount of water vapor the air could hold if it were saturated. So the amount of water vapor in the air divided by the water vapor capacity, the amount of water the air could hold. We multiply by 100 just so that we can express it as a percent. So again, relative humidity is telling us how full the air is with water. And notably, since the capacity varies with different temperatures, the relative humidity is going to be really temperature dependent. Pause the video for a moment, get that equation for relative humidity in your notes, and make sure that you truly understand how relative humidity is a measure of how full the air is with water compared to its capacity to hold water. So again, relative humidity is a very important concept. We know that it measures how full the air is with water, basically how much water vapor is in the air, divided by the capacity for that air to hold water. So it's telling us how close, as a percent, the air is to saturation. So how might the relative humidity change? Well, there's two ways that it could change. Let's look at the equation. First, more water vapor could be added to the air. If the capacity stays the same and you add more water vapor to the air through rain or some other mechanism, the relative humidity would increase. That makes good sense. Second, and importantly, the water holding capacity of the air might change. If this number here were to get bigger or smaller, even though the water vapor in the air stayed the same, if the denominator changes, the relative humidity is going to change. So when does the water holding capacity of the air change? Well, it changes when temperature increases or decreases. We already looked at this figure, 6.7, and let's check it out again. This graph shows how the saturated specific humidity, so the amount of mass of water in a certain mass of air, can change with temperature. So as temperature increases, the saturated specific humidity increases, or another way of saying that is the water vapor capacity increases. The amount of water that the air can hold increases as temperature increases. Similarly, if temperature were to decrease, the amount of water that the air can hold also decreases. Say it one more time. the water vapor capacity increases dramatically as temperature increases. So the denominator here will increase as temperature increases. The air can hold more water. The higher the temperature, the more water the air can hold before becoming saturated. One way of looking at that is that the water holding capacity is directly related to temperature. As temperature goes up, the water holding capacity goes up. As temperature goes down, the water holding capacity goes down. But now, how is relative humidity related to temperature? Well, if this denominator is going up, if this number down here is getting bigger and bigger, relative humidity will be getting smaller and smaller. Let's work through a few examples using the equation shown here. Let's assume that the air contains 10 grams per kilogram of water. So that's the water vapor in the air, 10 grams per kilogram. And let's assume the air temperature is 24 degrees. Well, if the air temperature is 24 degrees, the water could hold 20 grams per kilogram. So what is the relative humidity? 10 grams of water per kilogram of air divided by 20 grams of water per kilogram of air, multiplied by 100, 50%. The air is at 50% capacity. The relative humidity is at 50%. What happens as temperature increases? Now let's assume the temperature is 32 degrees C. The amount of water vapor in the air is still 10 grams per kilogram. But now it's warmer, 30 degrees, or 32 degrees C, excuse me. And the water holding capacity is about 30 grams per kilogram. So 10 divided by 30, the relative humidity is now 33%. As the temperature went up, the water holding capacity of the air went up, so the relative humidity went down. The air is not as full of water at this higher temperature, even though the same amount of water is present in the air. Let's do the reverse and assume we have the same amount of water in the air, but the temperature drops. Maybe it's getting close to evening or nighttime. The temperature drops to 20 degrees C, and now the water holding capacity is only 15 grams per kilogram. So as the temperature went down, the water holding capacity of the air went down. Now we have 10 grams divided by 15, 67%. So as the temperature went down, the water holding capacity of the air went down. Thus, the relative humidity went up. So the most important point to note here is that temperature and relative humidity have an inverse relationship. As temperature goes up, relative humidity goes down. As temperature goes down, relative humidity goes up. That's super important. Intuitively, you have some understanding of this because you may notice in the evening time, as the temperature is going down, the air seems more moist around you, even though it hasn't rained. Let's continue this example and have the air temperature drop even further. It started at 24 degrees C, then it went to 20, now it's going to go down to 15 degrees. Well, at 15 degrees, the air, can only hold about 10 grams per kilogram. So there's only 10 grams of water per kilogram of air that can be held, and that's how much water was in the air. 10 divided by 10 is 1 times 100. We have 100% relative humidity. Now the air is saturated. And interestingly, this is the only time that condensation can begin, when the air is saturated. So in the evening time, perhaps you start to see dew forming on the grass or on your windshield. Condensation can only occur if the air is saturated. I encourage you to pause the video and review these examples, both the math and the general concepts. To review one more time, there's an inverse relationship between temperature and relative humidity. As temperature increases, the water holding capacity of the air increases. That's a direct relationship. But the relative humidity decreases. That's an inverse relationship. Similarly, if temperature were to decrease, we would expect the water holding capacity of the air to decrease, and thus the relative humidity to increase. Again, very important concept. So you should be able to fill in the blank on this statement. When you have an unsaturated mass of air, meaning it's not full of water yet, if you cool it, what happens to its relative humidity? Hopefully you note that as you cool an unsaturated body of air, you're increasing the relative humidity. And if the air cools enough and the relative humidity increases enough, you might actually eventually get to 100% relative humidity, the point where the air is completely saturated. And at this temperature, as you went down and cooled the air, this temperature would be called the dew point temperature. That's a very descriptive term. It's the temperature at which dew starts to form. It's the temperature at which the air has reached 100% relative humidity. When dew forms, it's a visible expression of condensation. So condensation can only occur when the air has reached saturation, or 100% relative humidity. This is when clouds form, this is when dew forms, this is when fog forms. Now let's look at how this plays out over the course of a day. See figure 6.8 from your textbook, which is shown here. Temperature is lowest right before sunrise. Notice at this time, when the temperature is very low, the relative humidity is very high. Perhaps some days it's actually reached 100% relative humidity, and maybe dew has started to form on the grass. As temperature increases throughout the day, you'll notice that relative humidity decreases throughout the day. It begins to feel drier and drier. In the mid-afternoon, it feels quite dry. As the sun gets lower in the sky in the afternoon, however, the temperature goes down, and as the temperature goes down, we know the water holding capacity of the air decreases as well, so the relative humidity starts to rise. Pause the video and go through this diagram on your own, noting the relationship between temperature and the water holding capacity of the air, and also between temperature and relative humidity. Lastly, for this particular day shown here, did dew ever form on the ground? Why or why not? Lastly, let's check out these remote sensed images from the National Oceanic and Atmospheric Administration. The image on the left is the one I showed previously that shows specific humidity. So the mass of the water compared to the mass of the air. Not surprisingly, the places that have the highest specific humidity are near the equator, where higher temperatures are driving evaporation of ocean water and creating more moisture in the air. The image on the right here shows relative humidity for the same time period. You'll notice that near the equator, the relative humidity values are actually quite low. Why is this? There's a lot of water vapor in the air, but the temperatures are also very high, so the water holding capacity is very great. So the relative humidity is quite low. The air is not that full of water. It could hold much more water. Thus, near the equator and in the tropical areas in January here have fairly low relative humidity, whereas the higher relative humidity values here, the oranges and the reds, are actually located in the mid-latitudes. They don't have as much water vapor in the air, but because they're cooler, the effective temperature here decreases the water holding capacity of the air, and these regions have fairly high relative humidity. So this example shows how temperature can affect relative humidity values around the world. So now we've covered evaporation and humidity. In the next clip, we're going to look at condensation. When the air reaches 100% relative humidity and it's saturated, we know that's when condensation can begin.